Yeah, I think we can begin. Good evening, everyone. So this is our 12th and last problem solving session for the course Nanomaterials and Their Properties. Like, mm, there won't be an animation session this time. Maybe the other teacher might be conducting a survey session. Okay. So this week, Professor covered uh, different applications, like different types of nanomaterials, mainly carbon-based. So we have three types of carbon allotropes. The first is a buckyball, which are also called fullerenes C60. So they're kind of football-shaped nanoparticles made of 60 carbons, C60, with the hexagonal and rings which form the pair. Next, we have single-walled carbon nanotubes. It's made up by folding up a graphene sheet into a cylindrical form. As he has shown how buckyball is made. So you have a pentagonal shape and there are hexagonal rings attached to it, and the angle is not perfectly 120 degrees between them. And when you fold them up, they'll join. That's why this is- If you cut them and lay them flat, there will be some space between them. There are different types of uh, carbon nanotubes. You can have single wall, single wall CNT, or this is double walled, or you can also call multi walled CNT. So there are different techniques to grow these CNTs: laser vaporization, arc discharge, CVD. Laser vaporization, you can get single wall nanotubes, 22 nanometer diameter. They're really good uniform size and very low defect. But this process is quite expensive. So we have graphite and how you get graphene out of it. So yeah, CNT here is a type of 1D nanomaterial. Because one dimension is more than 1 millimeter. Appreciate in the graphite on the other hand are stacked layer of graphene. So graphite are different layers of carbon atom bound to each other with pi bond, weakly interacting pi bonds. So you can separate them, break these pi bonds using different methods, and you get a single graphite sheet, which we call graphene. Has hexagonal structure, and there are many different ways you can. The first graphene discovered was through mechanical separation, where they used Scotch tape to separate out layers of graphite. You can have exfoliation, where you introduce some molecules in between, and these molecules will increase the spacing, and eventually, if you have sufficient number of molecules in between, they will remove individual layers of the graphene. There are different types of graphene. So that depends on how you're folding up this graphite sheet. So if you join this carbon atom with this one, you have this pattern, which is your zigzag TNT. So it will form fold up like this. So you can imagine this side. So here you see this zigzag structure. Okay. You go around along the diameter of the tube. So this is your zigzag along the diameter if you see. You see this shape. In armchair, you fold the graphene along this direction. This you join this atom with this, and you get this shape, which is called armchair shape. Armchair. Here you can see this structure here. It, this is armchair and this is zigzag. And if you do join any uh, position in between, like if you join this atom with this, this with this, anything in between is your chiral CMP. Spiral because it has a rotation. If you see down the spiral, it has like this is clockwise rotation, right? If you take the mirror image, it will be anti-clockwise, so not the same. So I'm calling the different ways of growing carbonated. You have your reactive gas, so CH4 plus inert gas, carrier gas, argon. You heat it up by heating, you're breaking CH4 into carbon plus hydrogen. This carbon would deposit itself on the catalyst surface, giving you carbon molecule. In the excess gases, hydrogen and the argon get removed by the law of gas. Graphene is relatively new discovery. 2004 only. So graphite was discovered very early, 1800 AD. Then we have 1986 when buckyballs were discovered. One day, in 1991, you had carbon nanotubes discovered. And in 2004, we discovered FT. So carbon allotropes can have any shape, any dimensionality. 0D, 1D, 2D, 3D. 2D was the most recent discovery. So there are different methods. You have a graphite, you can oxidize it, graphene oxide, and they get these layers will separate and you get reduced graphene oxide. This is already available commercial type of graphene, sorry. You can use liquid phase exfoliation where you have ultrasonic waves which break down the bonds between the layer. You get removable graphenes. You can have electrochemical exfoliation where you use charge to separate out the layers. Next, we have chemical vapor deposition technique of making graphene. So you have your nickel substrate, which is acting as a catalyst. You introduce your methane gas and you heat it up. By heating, this methane is broken down into carbon and disolate, which is hydrogen. This carbon will diffuse onto the surface due to heat, you form the structure, and as you cool it down, you get nothing on the surface. There are wide variety of applications for graphene. They have this thing is called aspect ratio. Yeah, this is a length by diameter. So this, depending on different aspect ratios, you can have different applications. So you can have hybrid materials where the graphene is coated with other material to make you can active material, or you can have flexibility. You can mix it with clothes to get conductive clothing. You can use it for uh, chemical separation, storage, fiber-based electronics. You have artificial muscles. For this, machine are very good thermoplates as well. In food and dairy industry, you can have enzymes on the surface of the graphene, which convert the lactose into glucose or galactose. Then electrochemical soil sensors, then for biofuel catalyst, water purification, these graphene tubes have very high surface area to volume ratios, which is why ample surface area for anything absorbing, purification, catalyst surface. This graphene has again quite a few similar applications, but using sensors, energy retention, contamination testing, there's graphene membranes, medical protective coating. So you can have graphene composites, foams, films, paper, fiber, and cloths. Can be used for actuators, sensors, capacitive sensors as you can charge the graphite. You have your parallel plate capacitors structure formed by the graphite sheet, piezo resistor, optochemical, triboelectric, where one surface of the graphene is rubbed against another material and generates electricity, lots of applications. Next, we have polymer nanocomposites. So, some brief things about polymer. Below a certain temperature, polymers behave as glassy, where they are in a relatively hard state. But as you heat them up, as they cross the glass transition temperature Tg, they start becoming soft, and after a point, they become rubbery. As you cross the glass transition temperature, they start to basically flow. You can mold them to differentiate. Electrical percolation of polymer composites. So you have your conductive nanoparticles in the polymer. So polymer are usually insulating. You have your conductive nanoparticles in case they're forming a pathway for electrons to flow. Conductive. Conductive. There are different classifications for polymers. It can be thermoplastic or thermoset. Thermoplastics are which can be reheated multiple times to change their shape. Thermoset is once you form them first time, if you try to heat them again to reshape them, they degrade into gases or whatever material, gases instead. So you can once you've made like set made something out of thermoset polymer, you cannot remold it using heat. Whereas thermoplastic, you can use heat to reshape it into new material. This also has, and so every time you reshape it, it degrades a little bit. There are limited number of cycling you can do in the plastics. Elastomers, again polymers which have like chains which can slide past each other. Rubbers, on basis of how they're linked, you have your polymers classified as linear. You have the polymer chain, branched, where the main chain has side chains attached to it. Loosely cross-linked, so there are main chains, and there are few interconnects in between, and then tightly cross-linked. So now main chain, these chains are very tightly cross-linked to each other. So this is much less like elastic or rubbery. No. Depending on different type of polymerization, so you can have homopolymer, or you have copolymer. Homopolymer is just same. So this is ethylene and ethylene unit cells linked together to form your chain. Ethylene chloride. Okay. Then you have your copolymer where you have different chains. So this is ethylene and propylene. You can have ethylene and uh, butene or like anything, any two different unit cells. Polymers, you just combine them. Okay. But depending on how you mix them, you can have alternating. So one is so this if this is A, this is B. You have A, B, A, B. There you are random. There are some A, then B, then some A again, B, some A again. They randomly in series. You can have block copolymer where you have A on one side, B in between, and then A again on the other side. You can have grafting where there is main chain which is composed of all A, whereas the side chains are B, polymer B. Polymers can also be crystalline, but most of them only have some part which is crystalline. So as you can see, this is crystalline. The outside the region outside this area is amorphous. So you can have polymer nanocomposites, so here is polyamide tape with silicon oxide nanoparticles embedded inside it. You have carbon nanotube inside your polymer. These are agglomerates of carbon nanotube. You can have matrix and your uh, uh, nanotube doping. So you have the matrix and there are carbon nanotubes inside randomly placed. It can be directional or randomly placed and we like. And you have polymer nanocomposites. So this carbon nanotube, you have a polymer attached to it. Next, I just wanted to show you guys some of my work. So I work on MOFs. This year they got Nobel Prize for discovering MOFs. Three people, one from Japan, one from Australia, and from US. So this is a kind of MOF. So MOF is metal organic frameworks, metal organic frameworks. Why are they called metal organic frameworks? So they usually have like cage-like structure. That's a cube. Suppose you have this cube. Here you will have your metal and metal node sitting at all the axes, and in between are some organic compounds. Okay, can be benzene rings or long chains. They usually have carbonic carboxylic acid, carboxyl group at the end or amine group because they form make good coordination bond with metals, with your metal nodes and their organic linkers which interact with each other. So this form this open big cavity in between. So this is like kind of making a frame out of that. So it's metal nodes, organic linkers, and forming a frame. Members. So I'm working on conductive MOFs. So these are my linker, hexahydroxytriphenylene, that's 3-phenylene, and 6-hydroxy. Hydroxy is O in my case. So the 3 rings, 4 rings, and then uh, 4 group at the end. So this H gets removed. This O forms a bond with metal, which can be carbon, nickel, or copper. Forms a coordinate bond with B, C+2. And this linker joined to this metal. This linker again, this is forming a X-shaped structure. The metal bond X-shaped bond between the metal. And you get this 2D layer structure as they grow forms this one. So these 2D layers are stacked on each other, really similar to the graphene, weakly interacting with each other. And this thing is hexagonal, you get hexagonal shaped nanoparticles. This is some copper and nickel based HSTP MOS. So they have different ratios of this is purely nickel. This is purely nickel. This is purely copper, and this is cobalt. So nickel forms very small. This is 100 nanometer scale. Okay. The scale bar, so you can see they are very thin rods, so there are kind of 2D, 1D nanomaterials. Again, this diameter is 10, 15 nano, 10. These are all bimetallic, copper nickel bimetallic mass. Another frameworks I'm working on is again with NOx, zeolithic imidazolate frameworks, or ZIFs. Zeolithic imidazolate frameworks. Is, this ZIFs with particular linker, which is 2-methylimidazole, which is two nitrogens, and there is CH3. Okay. This is a hydrogen here, hydrogen here. These are all carbons. This linker, when it combines with zinc, forms this ZIF8 morph. Okay. What I'm doing is adding, so this is a block copolymer, polystyrene, block polyethylene. So the polystyrene chains in the red zone and the polyethylene oxide this way. So this is block copolymer, and they're mixed with this linker, which is 2-methylimidazole. This one. This forms this is spherical micelles. Then we add zinc to it. This smoke grows around this micelles. And when we remove it with THF, you get this porous structure. So we get this nice porous structure. You see all the porous and all the like micelles which we removed. And there are different concentrations of and different blocks polymers used. There are different uh, size of the holes and different density. As you can see, this is carbonized. So now, once you have this mock, you put it in tube furnace for 900 degrees Celsius. All of the mock is converted to carbon. Just we have carbon, and this has I think copper, some copper doping in it. And this has some of the zinc is replaced by carbon. There, some of the zinc is replaced by iron. So there is zinc and iron mixture. Once you carbonize it, you get structure with carbon and iron, iron with copper. At 900 degrees Celsius, most of the zinc is evaporated because it's made one time. And then you get this porous carbon. Mainly, this is transmission electron microscopy, HPEM. You can see the spores inside, somewhere inside. And this is just ZIF8, carbonized ZIF8. This is carbonized CU ZIF8. And this is carbonized FP ZIF8. So in case of iron, you can see there are carbon nanotubes going out of. We saw that these iron nanoparticles act as a catalyst for growing carbon nanotubes. Wherever these nanotubes start to grow, you can see there are iron particles. And this acts as a catalyst for graphene growth. Graphene nanotube growth on the carbon particles. Okay, now let's go through some practice questions. When and where was graphene first isolated in the lab? So it was 2004 in Manchester. Just remember, yeah. Which of its properties make graphene such an amazing material? So it has very good electron mobility, very good mechanical strength, very good thermal conductivity, so all of them. So it's a good conductor, as well as very good mechanical strength. When graphene was first isolated in the lab, which technology did researchers use? So they used scotch tape to peel off. So this is kind of mechanical exfoliation. Mechanical exfoliation. Okay. Which of these carbon isotopes can be found in graphene? So you have the graphene. So if you roll them up, so there can be defects as well in graphene. Maybe some high wind things. So if you just roll it up, you get carbon nanotube. If you try to make it in a spherical shape, you can get fullerene, but there will be some rearrangement of these some hexagonal into pentagons. If there are defects like graphene itself has pentagons, easier to form fullerene. And if you just stack these two together, layers of these graphenes together, you get graphite. All of them are graphene. Graphene is a so graphene is a sheet. Both these two dimensions are greater than x, y, more than 100 nanometers. It's a period area. Only one dimension with the thickness is less than 100. It's actually maybe one less than 1 or 2 nanometers. It's only graphene. What is the smallest atom that can pass through a sheet of graphene, defect-free single layer graphene? So these are all carbon, right? You can imagine the bond, the space in between is only few angstroms. So most of these bigger atoms, cerium is a big atom, oxygen molecule is a big atom, so they won't pass through it. So not even the smallest atom. Maybe helium, hydrogen, because they are very small, they can pass through, but nothing else passes through. Nothing. Carbon nanotube, you can have different shapes, I will discuss, zigzag, armchair, or spiral. So you have this direction. So if you fold along this direction, you get your zigzag shape. Make this shape zigzag. You can see it over here. You go around the diameter circumference. You see the zigzag, right? And you see this zigzag shape. If you go along this direction, you get your hair, you get your armchair, you go around the circumference, you get your armchair. Chair. Okay. And anything in between, there is combination of those two directions, you get your parallel CNT. So you want to see like this um, this one, these hexagonal rings are stacked vertically, right? In this one, they're at an angle, and also they are horizontally. These rings form horizontal. And here, these rings are at an angle. These are going at an angle, right? Here is horizontal. Vertical. Uh, you can see it at an angle, but this angle is fixed. It should be, I think, 30 degrees. This is 30 degrees. Okay. Chemical solution deposition is also, this is also called Solvay method. CVD is chemical vapor deposition. Again, technique to grow nanomaterial. CVD. Why do acoustic waves do not interact with nanoparticles? Is reason is because their wavelength is very large. The nanoparticle are within 10 to 100 nanometers. And the wavelength of these acoustic waves is much bigger than this diameter, so they will not interact with nanoparticles. In CNTs, both hexagonal and metamaterials are present. So this is true because in perfect CNT you would get hexagonal, but in CNTs you find in the lab or in real life, you have some amount of pentagon and hexagon. There you have a pentagon in between. It is the range of parallel angle in CNT. You saw it 0 to 30 degrees. So this direction, this direction. This was 0, 0, which is N1. Here again, degrees. And N 0, 0, N 0. Last scale production of CNT. So this is mostly done in tube furnace and the catalyst. 0 to so this okay. This is a tube furnace. nanotubes. MOF2 has the graphene-like structure. Um, Here we have MOS2. We have one only graphene-like shape. I think it's 2D planar. If you see it from the top, it will look like but if you see it from the side, it will appear this, this has some thickness. It's kind of like uh, graphene-like structure. Here, the compounds, all carbon-based compounds, graphite have the least stability. This is false. Graphite is quite stable actually. It's found naturally, so it's bound to be stable. When single layer of graphene are stacked together with on graphite, yeah, so that's how we got graphite and graphene in the first place, separating the layers from graphite. Permanent mold is made up of permanent mold is made up of usually metals. It's again polymer manufacturing method. Tightly crossing structure is found in 3D polymers. Tightly crossing structures. Polymer morphology and bonding between polymer and matrix and the particle strongly dictate efficiency of load transfer in the nanocomposite. So suppose you have your nanocomposite, you have your nanorods, and you are applying force interaction, interaction. These are nanorods, and they are not drawn to a portion. This is your matrix. So one of two things can happen. One, this nanorod, just suppose this sample breaks from the middle. One would be the case where the nanorods themselves break up. In this case, we have very good bonding between the matrix and the nanoparticles. Hooks and nano rod is top. Whereas the second case you can have is the nanorods kind of get pulled out of, won't be clean, but yeah, other side you see is not a thing. See cavity. So here, the nanorods got pulled out of this sample. So here the low transfer was poor. So main reason you're adding nanoparticles is to provide strength. So here there was energy required to break these nanoparticles, and these nanoparticles as the reinforcement, which are like tougher materials which require more strength to break. Whereas in this case, your nanoparticles were not broken, and just were pulled out. So this matrix nano interface is not weak, not strong, it's weak. Matrix and nano interface is weak. Okay, next we can discuss last week's assignment. If you have any questions till now, you can ask them now. Chat. We can see that. Okay, let's start discussing this assignment. First question: materials which are slightly repelled by magnetic field are known as. To slightly repelled, you need to have negative susceptibility, and they are the dimagnetic materials. So, called dimagnetic. Paramagnetic strongly attracted. They are also little weakly attracted, but not as weak as this. This is very weak compared to any other paramagnetic. Ferry and ferro are similar. All these are strongly attracted in the diamagnetic region. Quantum well quantization occurs in quantum well is something like this. So only in this direction get quantized. So only in one direction. Like the second dimension is large. Only this dimension is where does the wave function phi of the particle in one dimensional box have value 0? So this was your one dimension, right? So here x is equals to 0 and x is equals to L. There they are wave function psi 0 and 0. Everywhere inside box is incorrect. At the boundary It is 0. Ultimately, you'll have node or anti-node. Node will be 0. Let me go inside. At the center, definitely won't be 0. Anywhere inside the psi x will be greater than 0. Everywhere outside the box is 0. At the boundaries too, actually. Okay, this is asking any delta function. The probability is 0. It forms a standing wave, it will be 0. So this is your n is equals to 1 wave. So node. So here psi is 0 at the ends. No boundary condition we put x is equals to 0, psi is equals to 0. So we put these two boundary conditions. We did the derivation. Yes. Okay, so, but outside it's also 0. But it's talking about the boundary conditions and the nodes. That's right. So B. What is the potential energy V of a particle inside one dimensional? So V we assumed is infinite, V is equals to infinite here, V is equals to infinite here, and in between V is equals to 0. That's how we did the derivation. V is 0. Which of the following material is the most suitable for making core of electrons? Soft and hard, should be soft iron, which can get magnetized and demagnetized easily. It has a large area. You are wasting more energy magnetizing and demagnetizing than the H curve in this one. So H, so B. Here is an example of dash material. Here is a paramagnetic. Yes, most of them metal into this into the but, um, I think this is will be attracted to magnets and O2. Permanent magnets have large coercivity. Uh, this plot. So if you want permanent magnets, you want to have large internal magnetic field at the end, right? So you applied external magnetic field, this is H. So B, you apply external magnetic field, you reach saturation, and then you remove the magnetic field. Now, to measure how much, if it's a strong magnet, you'll require much larger H in the magnetic field in the inverse direction. Coercivity. Yeah. And coercivity and permeability has relation. Yeah, it's large. In soft magnetic material, why are domain walls more boring than hard magnetic materials? Answer is a low crystal imperfection or defect. So if there is any defect or imperfection that will hinder the movement of the domain walls, for soft magnetic material, you want them to easily magnetize and demagnetize. The domain should be more mobile. Change the crystal defect and imperfection that act as bending sites for the domain walls of magnetic material. These imperfections are minimized, allowing domain wall to move more freely under influence of light wave. Domain wall width is decided by support A and B. The width of the domain wall is primarily determined by the balance between exchange energy, which favors alignment of spin, and their magnetocrystallinity and magnetocrystalline amorphous energy, which favors alignment with crystal axis. What is the primary function of domain wall in magnetic material? To reduce the magnetostatic stray field energy by aligning spins in different directions. Thin magnetic films. Thin magnetic films with perpendicular magnetic anisotropy. What are the two primary types of domain wall described in the context of? There are two, if you remember, Neil and Block. One was where your magnetic domain moves in plane of the wall. Another was where the magnetic field moves outside. These all the vectors are same length, but just seeing it rotated outside the plane. To block and Block wall has spinning rotation in plane of the film. These are block. Wheel has spin walls. Wheel wall has spin rotating out of the plane. Read out so far. What's already discussed? Last year, student asked me the question paper is going to be. So last year it was partly objective and then subjective. So this is our last session. But, there won't be revision session. Maybe the other TA might take one. Here's the exam. Online computer based exam. Hall ticket is not yet released. Date and so on. Yeah, announced. So you'll get the address of the exam center and the hall ticket. Maybe this month or next month, October, November. Yeah, so briefly discuss type of questions they asked. There were, I think, um, I think there's faster 20 marks for objective. It may or may not be same, but it last year. So there will be objective and subjective type. If it's anything about last year, prepare for both objective plus subjective. And questions, objective types, there are four options, or you can also have true and false, and 1 mark or half a mark. Then there were some subjective questions as well, like uh, this 10 mark question. Holy grail of material science and engineering in the selected field. Related finding of strength and equilibrium data in material. So determine the Hall Fetch equation relating yield strength and of the material in grain size. So you had to do the derivation of the Hall-Fitch equation. Sigma equals to sigma naught d to the power d to the power. Right? You need to do the complete derivation of this equation. So let's say do all the derivations, memorize the derivations. The one I did particle in both kind of derivations. Remember those, remember different definitions. The question last year differentiate between super paramagnetism and paramagnetism, super paramagnetism. As you know, yeah, as your grain size becomes very small, the first entry or super paramagnetism, magnetism to draw all the diagrams, how the velocity is changing, the particle size, and those things. I also mention approximate range of these particle size, grain sizes. If, what effect is the grain size on coercivity of magnetic field? So this is the diagram. When it comes to crystalline anisotropy, and how does it affect the magnetic properties? So there will be some subjective questions. And there was what are the properties of nanomaterial providing which provides driving force for diffusion. It is one question. There is the expression for vacancy concentration of nanomaterial with particle size. So you know when this or derivation done in the class, calculating the vacancy concentration. First few classes with the particle size. So remember these derivations. Definitions. This is this is just from the last year. Maybe questions may be different. Okay. Only the slides in the PPT I upload. It will be recorded. That's it. There anything else? I can maybe briefly discuss it. There's 12 assignment as well. Pure iron at room temperature is dash uh, iron is um, the d orbital is partly full, so there are some unpaired electrons. So it will have some moment. I won't take the answer. And yeah, even the assignments, uh, there will be some either there will be averaging or there might be some like they will take best of the some of the assignments. No, so last year they did best 8 out of 12. Can be similar this time too. I am not making the question paper, making these assignments, not doing this. What I'm just telling what happened last year. Look at last date of the 12 assignments. Direction of easy access and single pistol. You can see should be in order to keep domain wall image smaller, domain wall should be kept thinner in order to keep monitors. People this compare over distance scale the exhibit to the parameter, but even though this interface even though it's not real size because there is multiple domains and multiple domains in the same range. There is very range in the domain. And so based on that, so for parametric model, what happens to monetization in absence of magnetic field? So this paramagnetism, so they're all randomly oriented. So how do coercivity and resonance and relation change? So coercivity already seen this was a plot of coercivity. This we already answered. Polygon morphology, bonding between polygon matrix and particles from also real this. Practice questions. CMT is incorrect. Incorrect. Interlocking, I think is same. I think Google, which is correct. Right. Which property accounts for stable, suitable supercapacitor? Both. I think related to this. But all the other answers same. This is false. This is false. This. Okay. Okay. Thank you, Matani. Stop. So, nice.